thanks. I'm happy, I guess, to open this workshop. Yeah, so I prepared this talk on Saturday when I came to this alumni meeting for Wolfgang, and I thought, like, okay, what I prepared this sounds great. So now I'm less convinced. Nevertheless, let me explain to you why I want to talk about this particular topic. I mean, it's very recently on the archive, and it's been sort of an ongoing thing for quite some time, so I'm happy to talk about it in any case, but also, this is largely motivated by an open question that was remaining after my PhD thesis, so this is essentially a topic about my thesis. So I gave a talk about a version of things that will come up in this talk 6 years back at this senior trimester program at a workshop. I think at that point it was called like 2 complete L theory of complex algebras, and so this is what came out of that thing. So I wanted to talk about this topic because it's an actual like direct sort of mathematical child of this concept 6 years ago. Okay, so what I want to do is just more or less explain some things or some aspects about the following 2 terms, and I'll just state them as they are, and then hopefully explain enough about the terms in the theorem so that you can take something out of it. And it says the following. So term 1 is the statement that there is a unique black symmetrical model transformation between 2 functors, so maybe let me call that thing tau, from real K theory to algebraic L theory, and I view all of these things as functors on the category of real C-star algebras to spectra, and I'll say something about what real C-star algebras are, and the statement is there's something called real topological K theory, there's something called algebraic L theory. Both of these are invariants of C-star algebras, spectra valued invariants, and there's a unique black symmetrical model transformation between these multiplicative theories. And the induced map, so this transformation induces a map that describes the algebraic L theory in terms of algebraic K theory. So this is a map of this sort. So let me write KO for KO of R. Write this somewhere. That's just the connective topological K theory, real connective topological K theory, and then there's a comparison map from this tensor product to L of A. And the statement is that this map is invertible. So you can recover the algebraic L theory of A by understanding its connective topological K theory, understanding this KO module L of R, and take the base change. A spectral description of this spectrum L of A. So in some sense, if you don't know what L theory is, and then, well, this is what it is, you only need to know what that module is. But I will say something about it, of course. I want to advertise this term because it allows us not to only describe the L spectrum, but in fact we can, from this theorem, give a presentation of all the L groups in terms of topological K groups. So this is what I think classically has been done. People try to understand L theory of C-star algebras by understanding their homotopy groups, the L groups in terms of topological K groups. And this was sort of a thing that you could do over the complex numbers and was not achieved over the real numbers. So what we do instead is to say, well, spectrally there is a formula that works sort of equally well for real and complex algebras, and well, now you have to find out how you present the homotopy groups of the left-hand side by means of this term, and that's not a complete tautology, also not very complicated, so let me also write it as a term, which is it's a consequence of this spectral statement. So term B says that for all C-star algebras A, we have canonical isomorphisms. Okay, let me phrase it in the following way. So the zeroth L group is isomorphic to the zeroth topological K group. So that's good. The first L group you can write as the first topological K group, and then you have to modify it. You have to divide out the action of eta, so this is the coterm of the map, which is multiplication by eta on KO. And okay, I'll say some things. So L2, you can describe. So I think that there's now one thing that's a bit funny, so you have to change a 2 to a 6. But let me also say right away that L is 4 periodic in a natural way. So L10 of A, or it's not even better, like L star of A is an L star of R module. I mean, as it must, because else the statement will not make too much sense. So this is a module, and the graded homotopy ring of the L theory of the real numbers is just a non-polynomial ring on a degree 4 invertible generator. Okay, so I mean, I'm describing sort of 4 L groups, and I choose randomly the 4 numbers 0, 1, 2, and 3. And there's sort of a better way of writing it for an n, which depends on its value modulo 4. And okay, but what comes out is that sort of if you want to describe 2, then sort of it's more naturally described as k minus 2. I think the L minus 2 is described as k minus 2, but okay, this is how it comes out. So you have to take k06 of A, and then in it you take the eta torsion, so which is the kernel of the map, the eta multiplication. And okay, since we're already here, let me also this time try to correctly write down what the homotopy groups of KO are. So KO star of A is of course a KO star module, and KO star. Okay, so what is that? Or maybe let me do it periodically. Nothing really changes. So that's a polynomial. Okay, so you have a generator eta, you have a generator x, and you have a generator called beta. That's invertible. That's of course the real Bott element. Eta is the eta we know from stable homotopy theory is a degree 1 element. X is a degree 4 element, and beta is degree 8. Okay, so this is an invertible element that's real Bott periodicity. Eta is the usual eta, and X is some preferred element. Maybe not preferred element in degree 4.
Not writing relations.
Ah, yes, of course, not doing it correctly. So last time I gave this talk, I at least wrote down relations, but I forgot half of them. So like 2/3. I don't know. So okay, let's see. So we have relations. Thank you, Thomas. So eta cubed is 0. 2 eta is 0, and eta x is 0.
X squared.
X squared, yeah, thank you. Okay.
Oh, that one.
X squared is, oh, I also did that one. So that was 4 beta. Yes, that's 4 beta. Is that right? Yeah. X squared is 4 beta. Okay, good. The audience is paying attention. I like this. Good. Okay, KO star is some ring which receives a canonical surjection from the thing where you don't divide on anything. So acting by eta is something that exists. Okay, good. This is what it is, and L3 of A. Now you can, well, okay, so this is what comes out. L3 of A is canonically isomorphic to K07, or K minus 1, if you would. Okay, so there are these isomorphisms, and let me say in words, and only make this more explicit either at the end of the talk or if you press me, that this map from K theory to L theory under these isomorphisms must correspond to some map from the KO group to the corresponding KO groups on the right-hand side. And they're essentially given by, well, you know, in degree 0 it will be the identity, in degree 1 it will be the canonical quotient map. Now in degree 2 and 3 it cannot be something like the identity or an inclusion or something because the degrees change, but luckily we have a degree 4 element with which we can multiply, and then you just check that you land in these groups, and this is what happens. Okay? So essentially these maps are induced by suitable multiples or powers of multiplication by this degree 4 element x.
Is there a decoration here?
Ah, yes, I should also make that more precise for those who know already what L theory is. So that's, I think, a number of words. Okay, so the rest of the talk will be spent trying to explain what goes into proving theorem A and how you deduce theorem E from it. So let me before explain some things. So just as a technical point, L theory is symmetric and projective L theory. So that means decoration, I don't know what people call it, P or 0. And that's the crucial thing. There is, okay, I'll remark this in a moment. Let me think. Okay, so before I want to do this, I think I want to say what real C-star algebras are, because there is a chance people know what is, have seen the definition of the C-star algebra, and typically it's done over the complex numbers, and there are some glitches over the real. So let me just say a C-star algebra. So this is implicitly over the reals in this talk, it's a real and involutive Banach algebra. Okay, so it's a real Banach algebra equipped with an involution. So the involution is anti-multiplicative, and because we're over the reals, you don't. I mean, it's just real linear. Over the complex numbers, you would require this involution to be anti-linear, complex anti-linear. But okay, this is not a complex algebra, so there is no such requirement. So it's just a Banach algebra equipped with an involution over the reals, such that two properties hold. On the one hand side, you need the C-star identity. Or for all elements, if you apply the involution and you multiply with x, you take its norm, then it's the norm squared. That's the C-star identity. And over the complex numbers, we would be done. This is the usual definition that you have. And now we have a further definition, namely that for all x in A, we have that the element 1 plus x star x is invertible in the unitization of A. Okay, so if A has a unit, then you can forget this. If A does not have a unit, then it doesn't make sense to ask whether something is invertible. But this element lives in the unitization. You can ask it to be invertible. And this is mainly done to say that if you take the complex numbers and equip it with the identity involution, that looks like a real involutive Banach algebra, but it does not satisfy this condition, and so it's not a C-star algebra. Okay, so it does satisfy this condition and this.
You said it's mainly done to exclude that example.
Yeah, I think that's more or less. This is sort of something that you don't want to be a C-star algebra. Like complex numbers with the identity and.
Is there a brief way to say why?
Yeah, I mean, sort of you need these kinds of arguments to have the right analog of all spectral theory arguments.
I think actually it's very interesting. Historically, this was even included in the first definition of complex C-star algebras, and then it was proven that it's a consequence of the first one. So that's why it's spread often on the spectral calculus.
Yes, and I think maybe in many things you can also get away with. You can sometimes get away with less than this if you require more on that side. Maybe you do this for all matrix algebras also, elements in matrix algebras. This is also something people do. But maybe I think I want to say that, I mean, C-star algebras have a sort of an algebraic structure. The norm is very compatible with the algebraic structure, and then you don't want C as a commutative frame to be a C-star algebra. That's all the ones. Okay, so maybe let me do some examples. So if A is a norm and star closed subalgebra of the bounded operators on some Hilbert space, then this is a C-star algebra, and in fact all are of this kind. That's a statement that every C-star algebra in this sense has a faithful representation on some Hilbert space. So it is of that kind. So these are examples, that's easy to check, but in fact all are of that kind, that's not easy to check. But also irrelevant if you want to write down examples. Another example is that if X is it's a compact Hausdorff space with an action of the group C2, then you can look at the algebra of functions on X with complex values, and you let C2 act on X and on C by complex conjugation, and you take C2 fixed points, equivariant functions. So those would also be real C-star algebras, and in fact any unital and commutative algebra is of this kind. Okay, so over the complex numbers, the statement is just every commutative unital algebra is functions on some compact Hausdorff space. Over the reals, the statement is not everything is real valued functions on a compact Hausdorff space, but it's complex equivariant functions on a C2 compact Hausdorff space. Yeah.
Is there like a theorem like what is it? That these are equivalents of categories, or
yes, in the unital case, this is an equivalence of categories. Yes,
that's correct.
Yes, in the non-unital case, you have to be a bit careful and pass to the correct subcategories on both sides. But for the unital, it's fine. Okay, and then maybe further examples that sort of come out in or appear in if you work geometrically, then it's some C-star algebras that you get out of a group of G group, maybe discrete. For here, there are also non-discrete variants, let's say a discrete group, and then these are completions, suitable C-star completions of just the real group ring. And for infinite groups, the real group ring is of course not a Banach algebra, so you have to complete it appropriately. There are many choices of such completions in general. And okay, there are different variants, and these things also appear in practice. And if you get bored with the talk, then it's a nice example and/or exercise to check what the values are. I don't know, there's only one such thing for the integers. Nice exercise in Fourier analysis to check what the complex
algebra several times.
Yes, I mean you can get greatly confused about this if you're a bit uncareful. So that's why it's a fun exercise. Okay, good. So this is what C-star algebras are, and the main motivation at the time of my thesis to compare K-theory and L-theory of these invariants was to relate conjectures that are about topological K-theory of these group C-star algebras and the algebraic L-theory of the real group ring. And okay, the algebraic L-theory of the group ring, it maps to the L-theory of the C-star algebra, and so you can hope that there is a comparison diagram. And so that was what was this old sort of theorem was about. So just as a bit of context, this is all in the vein of understanding the relation between Ferry-Jones and Baum-Cohen. More precisely after inverting 2, but okay, there's some things you can do. But this is sort of where this stuff came from. Okay, so that's one thing I want to know, or I want to say. Then I want to explain what was previously known about these kinds of results. So previously known, because I mean a good deal was known earlier. So something that was known is that the isomorphism from L0 of A to K0 of A, this was known for all A, and this is true for all Banach algebras. I mean, probably more general Banach, but let me just say convoluted Banach algebras. And I mean, this was mainly an observation. I mean, yes, this is what Karoubi did. So Karoubi, at the end of the 70s, wrote an annals paper about permission K-theory and used it to calculate some portions of the cohomology of things like the symplectic orthogonal groups over Z adjoint 1/2 from Z with certain coefficients. And in understanding these homotopy types appropriately to calculate cohomology, at some point he needed to understand something like what is the L-theory of the real numbers as a spectrum. Something sort of implicitly he needed to do. And in that world, he analyzed these things, and this isomorphism was done. Yeah.
We need a C algebra.
Yeah. Sorry. Yes, maybe. Yes, sorry. Okay. Let me just say this. Sorry. Yes, you're right. No, of course you're right. Yes, no. You need something. But okay, this is true. And Karoubi did it for C-star algebras, or maybe a bit more general. Yes. Okay, so this is correct. So what Thomas and I, okay, I'll do it like this. So we showed that theorem B is true after inverting 2 everywhere. And I apologize. So theorem true is true after inverting 2. That's also true essentially. Or maybe we should add Rosenberg. He also wrote up Jonathan Rosenberg. So somehow, if you neglect 2 torsion, or if you invert 2, then essentially everything was known. And theorem A was sort of is also true, and that's what I did with Thomas or in my thesis. So essentially, what we proved is that if you invert 2, this map of algebras is an isomorphism. And so in particular, that spectrum is equivalent to that one, and that is what we earlier proved. And we didn't write down the spectrum value version of this theorem A for complex algebras, but so this is something we proved. And it was earlier known that theorem B is true for complex algebras. Okay, so if you have a complex C-star algebra, it turns out that the L theory is 2 periodic, as is the K theory, and eta acts trivially. So taking eta quotients or eta torsion just doesn't do anything, and you see that all K groups are isomorphic to L groups. And this was done using something a bit more. So in fact, you can do something like what's called free L theory of a real C-star algebra. Say if A has a unit, so if A is unitive, then there's a well-defined way of thinking about L theory with free decoration. That just means we don't think about forms over projective modules, but forms over free modules. And you take an appropriate L theory in that sense, and this was always described that this is isomorphic to the real K group, and then you mod out the subgroup generated by eta. Now that A has a unit, eta is an element in K1 of A. Because the real is mapped to A, and so eta maps into it, and there's a subgroup here. It's also something that Hausdorff proved, and something of that nature might have also been done by Miller. Okay, so with some concrete models of what these groups are with free decoration, people had shown that the K group and the L group are isomorphic if you have a complex algebra. So in that case, you don't have to model by eta because eta is 0, and in that case, it turns out that free and projective L theory in degree 1 for complex algebras are the same. It's not an argument you have to make, but so there's a variety of things that was known before. But no uniform picture was understood, no spectral version was available, I think, and also no real conjecture or idea of what the higher L groups would be, how you describe them in terms of K groups, without inverting to or without restricting to complex algebras, in which case periodicity tells you what happens. Okay, so this is, I think, more or less state of the art. Any questions about this? Then I want to tell you a bit about things that go into the proof of these terms. Ingredients, say. Okay, so we can all remember that L star of R is just a polynomial ring, and I cannot remember what this is, so we have to just think about it every time it's important. Okay. So let's say something about proof ingredients. And in the course of these proof ingredients, so I've chosen not to give a formal definition of what L theory is, but in the course of the proof, you will see some presentations of it that are not made in terms of this term, but in a different way. And this is the thing that we'll actually use on. So you can take it as a definition, or if not, then I can tell you something more about it later. So there is a theorem that will contain many sort of bullet points, and I'll try to write down names to say who these bullet points are due to. That will be sort of central in our argument. So the first thing is that there is a category. I don't know how to write this. So I want to say there is a stably symmetric monoidal infinity category KK, which is a symmetric monoidal Dwyer-Kahn localization of C-star algebras. Okay, so the statement is that there is this category of C-star algebras, and it comes with a functor to a stable infinity category KK. This functor is symmetric monoidal, and it is given by universal property in the sense that you can recover this category, by taking all elements here, all morphisms that go to equivalences, and formally inverting them. And then what happens is that this set of morphisms that you have to invert just satisfies some nice properties. It's sort of compatible with the tensor product of C-star algebras, and it's compatible with something called a fibration structure that you can put on this that you can use to show that the localization is a stable category. This is not at all obvious, and I mean there are many names that you have to put here, and I guess Kasparov is the biggest name because he invented this category, essentially. Not phrased like this, but essentially this is a construction due to Kasparov. But I mean, for our purposes, sort of the formal properties are the things that are relevant. So C-star algebras come with a functor to KK, and this is a stable category, and this, whether or not a functor from C-star algebras to something factors over KK is a property. That's the thing to take away. And one further important thing is to do is that if you look at the following thing, so there is a functor from C-star algebras to spectra that I call KO theory, and you can take its connective cover, then you get this connective topological KO theory. And the statement is it factors through KK in a very specific way, namely such that the functor through KK is just the thing that's co-represented by the tensor. Yeah, that's the statement. So if you want to understand something about K theory, well, because it's a KK-invariant functor, you can just study it through the eyes of KK theory, and then K theory becomes co-represented by an object, and it's easy to study transformations out of it, because it's easy to study transformations out of co-represented functors. So that's one crucial property that this KK category gives you. Then, let me put this below here. It's a consequence of a work of Thomas that resultingly KO and KO are the initial objects in the category of either exact functors that are lexemetric model from KK to spectra and product preserving functors that are lexemetric model from KK to spectra. So as lexemetric model functor, periodic K theory and connective K theory have a universal property, or initial in some category of functors, and in particular, if I want to prove something that there exists a unique lexemetric blah blah blah, out of something that's initial, I just have to check that the object that I want to map to is an element in this functor. So that's the approach that we want to take. We want to sort of use KK theoretic tools to just get maps for free. Once we have a map, we can check whether or not this map is an isomorphic. We have to get a map in the first place. And I want to maybe highlight that if you think of models or any way of constructing the algebraic L theory of A and relating it to topological K theory of A, you sort of run into an issue that it's known, or we can prove that this is essentially the only way that you can map integrally between these two functors. There's no way no map in the other direction. There's no map if you don't take a connective cover here, so there's nothing from the periodic thing. This all doesn't exist. So this is the only thing you can do. But then you sort of run into the problem that this is constructed, if you think about it in terms of some actual model of spectra or so, it's constructed in a very continuous way, as sort of some configuration space of points labeled over your C-star algebra, whereas this is some sort of purely algebraic and combinatorial gadget. And it's sort of complicated to map something continuous to something discrete. But on the other hand, you cannot map the other way because there is no such map. So from our point of view, it's just very useful to use these KK theoretic tools, because you just have to check a property of L theory that you can do in any model that you wish, and then you get maps for free by means of these universal properties. And writing them down in an explicit model, I have no clue of how to do, but it's sort of also maybe not relevant for these kinds of applications. Okay, so that's what we have. And I also want to highlight, although it's not maybe terribly important, that so that's a further point. So this is Nikolaus, sorry. That's due to Thomas. And a further thing is, I want to say that if you have a functor from C-star algebras to D, where D is an additive infinity category, which spectra luckily are, then you can characterize what it means for a functor to factor through KK. Then F factors through KK even only if, originally 3, but sort of a posteriori 2 conditions hold. So one, F is so-called K stable, and that means that F inverts a certain type of map, which is induced by, so K denotes the compact operators on Hilbert space. In there you have sort of many rank 1 projections, things that project to a rank 1 free module. And you can take this projection and it gives you a non-unitive map from A to this tensor product, and you can ask whether or not F inverts that map. The property, right? And this is a necessary condition for a functor to factor through KK, because this universal functor from C-star algebras to KK does that. You have to check this. And the second condition is that F is split exact. And okay, split exactness here means if you have a short exact sequence of C-star algebras that comes with a multiplicative split, you apply your functor, then you ask the resulting thing to be with zeros on the left and 0 on the right to be an exact split exact sequence of abelian groups. So in former times there was a third condition called homotopy invariance. You also need the function to be homotopy invariant, but it turns out it follows from these two properties. That's something that Hickson proved. So this is a term of Hickson. And it largely builds on the Kunz picture of KK theory. But in any case, I just wanted to say, for the purpose of sort of psychology, that in some sense we understand exactly what sort of functors factor through this, and you can try to use this property. However, it's a bit annoying. Split exactness, for instance, is something that looks very algebraic. For L theory, you just check, believe me, for L theory, you just check that it's split exact. That's something that's in principle, like the tools of L theory are made such that this is something you can check. So this other condition is a bit more subtle, because this really involves sort of C-star algebraic procedures. This tensor product is not an algebraic tensor product, it's a completed tensor product, and the compact operator sort of, you can think of this as having an exhaustive sequence of sub-algebras given by the matrix algebras over A. The compact operators are sort of exhausted by bigger and bigger matrix algebras over C. So this tensor product is exhausted by bigger and bigger matrix algebras over A. Now, L theory is an algebraic tool. Again, it's made such that you can check that mapping into matrix algebras induces isomorphisms, but then you run into the issue that at some point you have to complete. And L theory is not made such that you're allowed to check sort of whether or not it does nothing to completions. This is sort of not what it's done for. And this is really the surprising thing, and I wanted to highlight this point because in principle it tells you how to show that something factors through KK, but that's not the thing that we do for L theory. Because we cannot check this property by hand, and it's some sort of a miracle that this is true, a posteriori. So we have to prove this differently. And the way that we do this differently is to exploit the following. So the main idea then. So we use that L theory as a functor can be written as a pullback of three other functors. Just because sort of you can do something converse in spectra. So you can take L theory and you think of it as a functor in spectra, and then you just invert 2 in spectra. And at the same time, you can take L theory and you think of it as a functor in spectra, and you complete that too. Also a perfectly valid thing to do. And then these glue together over taking the 2 completion, and then in that you invert 2. And that's just pointwise, and the pullback square in spectra, and everything is sort of natural. So this is a pullback square of functors. And I want to check that some functor has a property. The concept is that I'm allowed to check it on each corner. And I might have different arguments for each corner why it has some property. And this is in fact what we do. So we can use, this was sort of this old result I told you about with Thomas, that this is KO with 2 inverted, which we know factors through KK theory, as I told you, so it has every property that you want. And really what it's about, and this is sort of what I talked about 6 years ago in the case of complex algebras, is understanding this functor. What is the 2 complete L theory of C-star algebras? How can we describe that in a way that tells us something useful? And this, maybe, I want to do this? Yes, this is what I want to, okay. Let me clean the board. Oh no, let me do it differently. Let me put a term here. So this term is due to either #9 or Schlichting. So #9 are these 9 people who wrote a series of papers about Hermitian K-theory. And Markus Schlichting did this version of the term earlier, but so let me comment on it in a moment. So there is something you can do in general for any ring. So I apologize, and should have started out with saying that L theory is something that is defined for rings in for C-star algebras. It's an algebraic invariant, and you apply it to C-star algebras by just forgetting that you have C-star algebra. Just take the underlying ring with an involution. Associated to that, you have an L theory. And what is sort of proven in these results is that you can describe the algebraic L theory of a ring in terms of algebraic K theory, in some sense. So what you can do is that there is something called Grothendieck-Witt theory of a ring. For the purpose of this talk, think about it as the group completion of the category of symmetric unimodular forms. As K theory is the group completion of the category of projective modules. So now you just take, in addition, symmetric unimodular forms over projective modules. and you do complete that. For the purpose of this talk, this is perfectly sufficient to think about it. And then there is a construction called the hyperbolic form that gives you from a projective module a form, and that induces a map from K-theory to Grothendieck-Witt theory. And you observe that if you have a module and it's dual, then their hyperbolic forms are isomorphic, because so the underlying thing is given by P plus P dual. And the evaluation or co-evaluation map from P to its double dual gives an isomorphism between the form on P and the form on P dual. So really what you get is you get an action on the K-theory spectrum that sends a module to its dual, and this map factors to the homotopy C2 orbits, because it's invariant. And L-theory is the quotient of this construction. And okay, so Schlichting proved something like there are these spectra, and then he calculated that the co-fiber has the homotopy groups that are the L groups, and he didn't officially write down a map that compares it to L-theory, and sort of in this hashtag 9 series we sort of have an a priori construction of L-theory, that is the thing that people care about, and then we prove that there is the sequence. But in this situation, I think Marco already proved this. So why am I telling you this? It's because I want to say something more. If you take a hyperbolic form, and then you can forget that a form is associated to some module, you can just forget the form. So there is also a forgetful functor to K of R. But now if you have a form, it gives you an isomorphism from the module to its dual. So this map now factors through the fixed points. And the composite is the norm map. Okay. And the theorem that there's this fiber sequence tells you that there is a canonical map from L of R to the algebraic K-theory of R to the Tate C2, which is the co-fiber of the norm map. And anything algebraic always maps to the topological thing, because discrete things you can map to continuous things. So in our case, there is always going to be a map from the L-theory of the C-star algebra to algebraic K-theory of the C-star algebra to the Tate C2, and then you go to topological K-theory of that thing to this Tate C2. And this is the thing that we use for the two-complete version. Okay, so let me now erase maybe this part. We want to keep this. So theorem C is that for A C star, the map from L of A to connected topological K-theory to the Tate C2. This is a two-adic equivalence. Okay, so algebraic K-theory is a connective thing. I mean, in this world, algebraic K-theory is meant to be a connective object. And so connective algebraic K-theory maps to connective topological K-theory. And then you say, oh, and then it's equivariant for the C2 action, so you can take Tate C2. And the statement is that this induced map is an equivalence. And so in particular, consequently, L theory is KK-invariant. And by that I mean it factors through KK. And because it is split exact, something that you can check by hand, it will factor as a product preserving functor. In fact, factors as product preserving functor. And C star. Sorry. KK. So if you think of it as a functor on KK, then it has the property of sending products to products, because products are a certain type of split exact sequences in this non-unital world. And also, I mean, I chose to ignore that deliberately, but now that we're talking about it a little bit, it's sort of crucial to work with this projective version of symmetric L theory in order to have a well-defined version of L theory on non-unital algebras. You can always sort of, if you have an invariant on unital things, then you can try to extend it on non-unital algebras by just joining a unit and taking the fiber of the augmentation map. But then also you don't want to change your original invariant. So you need to know that if you plug something in that's already unital, then you need to check that you haven't changed your definition. If you have something unital, you unitalize, you just take product with R. So you want to know that you could be with products. That's something that this projective L theory does, and other types of L theories that would appear in Survey theory, like free or simple kinds of things, will not do this in principle. So for this comparison, it's just necessary to work with this projective version, and then you can get versions for free L theory from the projective one. This is the approach we take. Okay, so let me, instead of explaining to you how one improves theorem C, so let me say this is essentially a work of, now I have to get it right, Grothendieck-Witt, Schlichting, Weidel, plus an epsilon. So they prove something, and then you have to observe that something, in fact, also proves that. And this is what Marco explained to us 6 years ago. When I gave this talk about the complex version of that theorem, which sort of Thomas and I tried to prove by using that there is a comparison back from K theory to both of these things in a compatible way, and then sort of exploit this commutative diagram we have. Marco explained to us that you can give a different argument which does apply to real C-star algebras a priori. And it's sort of it's a cheap trick. So let me just say that for the experts, what you try to do is you cook up a theory of this sequence where you replace algebraic K theory by periodic topological K theory. In that world, you still get some version of L theory, and it will turn out to suffice to prove that for that version, this comparison map is a two-adic equivalence. Just by this is something you have to prove, but this turns out to be correct. Some version of cofinality. This is what it turns out to be. But in that world, somehow what happens is that both of these spectra, this analog of the L spectrum and the analog of the Tate spectrum, they're just both uniquely two divisible. So this is true for the stupid reason that everything is 0 mod 2. It's not very surprising that a map between uniquely two divisible spectra is an equivalence after modding out by 2. So to check whether or not this map is an equivalence mod 2, you can pass to this other world without changing anything where everything is already two divisible. So you sort of agree. And the fact that everything is uniquely two divisible is just one calculation you do over the real number. So once everything is a module over that, you just calculate here. So you explicitly see where you invert 2 in some process that appears in this world. And you can think if you replace algebraic K theory by periodic topological K theory, you've inverted an element at some point. You will also have inverted an element in this variant of L theory, and you just observe that that element was divisible by 2. And there you go. Okay, so this is somewhat of a formal thing. Okay, but that's the basic idea for this theorem C. So let me then spend the rest. The talks are 50 minutes, right?
We started late.
Yes, we started late. Okay, good. So I have 10 minutes or so.
Yeah.
Okay, good. Okay, so let me try to indicate how we want to prove this result. Maybe. Where do I do this? So let me use the following notation. If you have an invariant F on, say, rings with involution, like L theory or algebraic K theory, doesn't require the involution or something, then you can define a functor F top on say, I don't know, I'm just going to do it in the case of C-star algebra. So you can define it on C-star algebras by sending A to the geometric realization of applying F to functions on an n-simplex to A. Yeah, so continuous functions from an n-simplex to A, that forms the C-star algebra, and then you can forget that it is one. You take its underlying ring, you apply F, and then you see that that's a simplicial object, you realize it. That's a construction you can do, and because geometric realizations preserve fiber sequence, you will sort of formally get from this #9/Schlichting result that you can take algebraic, maybe I should say, you can take algebraic K theory and topologize that, and then maybe by no surprise you will get connective topological K theory.
We are taking a functor value is something stable, right?
Well, yes, maybe.
Whatever sequences.
Yes.
Can do it with spectra, but that's a different argument.
Yes, let's say with values in spectra. And you can do this construct. Yeah, let me be a little bit vague. But the statement mainly is that from algebraic constructions, you can topologize them by taking sort of realizations of these simplicial objects that you get from taking the algebra, the topology on A into account by taking continuous valued functions on simplicities. And the statement is, if you do this with algebraic K-theory, you get connective topological K-theory. And if you do it with GW, then you just get something that I call GW top. It's some topological version of Grothendieck-Witt theory. And it turns out that you can describe this thing as, say, the group completion of the topological category of Uni modular forms over projective modules over A. That's something that's true. So this is still something that's sort of true. And then it's a proposition, and this is, I think, really the basic and surprising fact that sort of makes everything in this whole theory work, is that the canonical map from L to L top is an isomorphism. So somehow, if you do this construction with L theory, you just won't change anything. So L theory apparently sees enough of the topology on A that this particular procedure of making it homotopy invariant doesn't do anything. And it's related to the fact that L theory as a functor is homotopy invariant in the strict sense. The homotopy equivalence of C star was that the L groups won't change. But okay, this is something that is true. And so from this #9 thing, what you get is a fiber sequence of this kind. And then here you're allowed to just write L away. Yeah. And so if I wanted to be very precise now, then I should either work with a connective cover of L theory here, or I sort of de-loop this topological thing as to make this a fiber sequence of non-connected things. And both is possible at curves. Your choice. Yeah, in some sense, what I'm writing here is correct. Okay, so this sequence you now have, and that's the thing that we want to use, because I mean, at some point I wanted to relate L theory to topological K theory and not to algebraic K theory. So this is the way that we get into it. We're allowed to topologize because on L theory nothing changes. Okay, so that's a good thing. And so as a consequence of this result,
I want to ask a specific question. You told us that it's not difficult to have K to L because L was discrete.
Yes.
Now you've made a non-discrete labeled version. I'm saying it's the same thing, so why is it still, you have a similarly nice story to tell about why it's still difficult to map it to L top?
Well, but L top is sort of a geometricalization of a combinatorial object. It's still not sort of doing something continuous with A.
Yeah, as you said, you can now replace the source by algebraic K theory.
I can now replace the source by.
Yeah, we can replace KO.
Yes.
Yeah, algebraic K theory. And then the map also exists.
No, I mean, you still need to take a projective module and flip it with canonical form.
And this is something you cannot do.
What you
cannot do algebraically, right? The map doesn't exist algebraically. It really only exists for C-star algebras or something of that kind. Okay, but okay. So the statement is that this is now a natural sequence of natural fiber sequence in A. This is still sort of a hyperbolic map. And okay, so I want to say what Grothendieck-Witt theory, there are different perspectives on it, but if we think about it as the group completion of the symmetric monoidal category of unimodular forms, then it will not come by any surprise that taking tensor products of forms equips that also with a like symmetric monoidal structure. And then doing things like geometric realizations will not destroy things being like symmetric monoidal. So this functor is still a like symmetric monoidal functor on C-star algebras. And this fiber sequence tells me that it's also KK-invariant, because topological K theory is taking orbits doesn't change anything. This is by theorem C, and so this one is also. So corollary is Grothendieck-Witt top is, for one, it's being a functor on KK is a property, as I said. It's a functor on C-star algebras, whether or not it lives inside functors on KK is a property. I'm claiming it's a functor on KK just by means of that fiber sequence, but also by means of theorem C. What you do is you check that it's a product preserving functor if you view it as a functor with taking values in connective spectra. Okay, so let me briefly say why that is. So this thing maps to something like little ko to the upper HC2, and that maps to little ko to the upper HC2. Now, little ko is a product preserving functor. No, actually, that's, sorry, I apologize. That's, sorry, I wanted to say something different. I apologize. I wanted to say it's an exact functor. I mean, it's obviously product preserving because that and that are. But what I want to say, in addition, it is exact, although this and this are not. But the reason that this and this are not, sort of, they cancel out, and what remains is something that isn't exact. And you can see that the reasons cancel out by precisely showing that, I mean, again, showing that a functor is exact is something you can do sort of one prime at a time. So I can prove it after inverting two, in which case, you know, these orbits don't do anything. And then this functor is exact, and I told you L theory is K theory after inverting two, so it's an extension of an exact functor, that's exact. But if you complete L2, well, I said that this is equivalent to taking K of KO. So by means of that completing this L2 is going to be little ko to the upper HC2. Little ko is an exact functor with values in connective spectra, and taking fixed points of that doesn't change that. So you can use theorem C to see that now Grothendieck-Witt is sort of a bit better. It's an exact functor and taxometric monoidal, and you can use that to run the following argument for the proof of theorem A. So you look at the sequence, and you observe that by the ko being initial, there is a tau hat, which is a laxometric monoidal transformation to Grothendieck-Witt top, such that if I go to L, this is tau, just by initiality. This thing is symmetric monoidal, laxometric monoidal. So there is a map, and the composite is still laxometric monoidal by something that I haven't told you what it is. So taking L from this is also a laxometric monoidal construction. So the composite must be the thing that I already had. So that's good, and it tells me that I get a commutative diagram that expresses a Grothendieck-Witt theory of A in terms of ko of A. And then I have to take over ko and Grothendieck-Witt of R. So I get that like this by the fact that this is a laxometric monoidal functor, and by the fact that this diagram commutes, I get a similar map here. And this is the map I want to show that's an isomorphism. And okay, what you do is you observe that the fiber of this map is of course given by ko of A tensored over ko with ko HC2. And then, okay, so the things that you do is you observe that the C2 action on the K theory is trivial. And that is for the reason that, well, it's induced by sending a module to its dual, but on a C-star algebra, every projective module has sort of a preferred equivalence to its dual. You can equip everything sort of with a more or less canonical positive definite form, like over the reals. Every vector space has some sort of unique positive definite form on it. Same is true for C-star algebras. And so that tells you that because the action is trivial, this term is in fact written like this. So this map is an equivalence, that's for sure. Okay, so you have this functor here, and you would like to show that it's an equivalence, but both of these functors, so this functor and that functor, are exact functors on C-star algebras, so it's going to be some formal argument that you only have to check it for A equals to R, because everything is exact, essentially. And maybe one thing for A equals to R, and you have to check that it's true on pi 0, so you have to check that Grothendieck-Witt 0 is in fact that time. And okay, this is a check you do once and for all. It's a statement about isomorphism classes of forms, and the statement is still that every form is decomposed into a positive definite and a negative definite part, and this shows, I mean, this you can use to show that that map is an isomorphism. So now you want to conclude that this map is an isomorphism, so the thing that remains to do is to show that this diagram commutes. Because else you're of course screwed. But then you again check that, I mean, this map, I mean, both of these maps are natural. So the resulting map from here to here is sort of a natural map in C-star algebras, and then just calculate how many there are. It turns out you only need to check that they agree on A equals to R. So again, the fact that these are essentially functors that are built out of things that are co-represented, built out of KO. And then sort of checking that these two are equivalent is again just by this universality of KK theory is essentially a check on A equals to R, where it's true by definition. So this diagram commutes, and you do compute that this map is an isomorphism. So this is essentially how this argument works. You show that L theory is KK-invariant. You show enough about it as to deduce that Grothendieck-Witt as a functor is not only KK-invariant but exact, which allows you to prove that it is given by that formula, It's probably something we can also prove by hand, I would imagine, but this is sort of the path that was natural to us, so this is how it comes out. And then as a consequence, you sort of get this presentation for L theory as the induced presentation of co-fibers. Okay, so this is how you show this term. So I guess I have no minutes remaining to tell you how to prove theorem B from it, but okay. So the statement is, from this description, you can try to calculate the low homotopy groups of that spectrum, and we'll come out with that thing. Yeah. I invite you to do that or to ask me how to do it, and we can talk about it later. It's sort of a fun thing. Okay, thanks very much for your attention.